Hello, I'm David Lam, Chairman of Multibeam Corporation. Multibeam is a proud member of the eBeam initiative, and we appreciate the opportunity to discuss an important eBeam topic. In the next 10 minutes, we'll examine the question, can eBeam lithography ever get into mainstream manufacturing? By eBeam lithography, we mean eBeam direct write on wafer with no masks. We'll review this question in 3 segments. First, we'll look at the changes taking place in semiconductor lithography. Second, we'll discuss how CVD and etch today improve pitch resolution that is not attainable by optical lithography, and how eBeam direct write can help finish the job to reduce the cost. Third, we'll examine the missing link Multibeam provides in the search for lower cost solution. As you know, eBeam resolution is great, but eBeam throughput is terrible. In fact, the low throughput has historically kept eBeam direct write out of mainstream high-volume fabs. So you may wonder, why are we still talking about a foregone conclusion? The reason is the lithography environment has changed in recent years and is continued to change. Lithography cost has skyrocketed, and our customers, the IC makers, are in need of a lower cost solution for the manufacture of advanced designs. And eBeam direct write, with the right approach, can play a key role in bringing down lithography cost. Now, let's look at the first segment, the changes that are happening in semiconductor lithography. Optical lithography has reached the resolution limits in about 2007, and this limit has driven the IC makers to adopt the unidirectional or 1D layout style to replace the conventional random 2D layout. 1D layout does not require design changes. So in the last 8 years, the leading fabs in both logics and memories has been producing in high volume of their devices using 1D layout. And this has spanned roughly 4 technology generations. Now 1D layout can split into lines and cuts. And the optical printing of the lines is very good, like printing gratings. But optical cuts will require multiple passes for each layer, and therefore driving up lithography cost. This is the daunting optical multiple patterning. Jan Brodowski of Intel famously presented this graph and showing the unidirectional lines as well as the cuts in order to make integrated circuits. With this example, he showed that it will require 4 masks in the 4 patterning steps. And that is something that would be very costly. Brodowski envisions that 2 lithography technology could work hand in hand and solve the problem and producing the patterns at lower cost. He also suggests that eBeam direct write could do the cutting of the lines printed optically and thereby complementing optical lithography. This leads us to the second segment. How Siebel, combined with CVD and etch, can help greatly reduce lithography cost. SAPD stands for self-aligned pitch division, or sometimes just called pitch division. It can reduce the pitch and increase the line densities and has been in use in high volume manufacturing for several years. Here's an example. Lithography can print 80 nanometers. That's the maximum, the smallest pitch it can print. However, using CVD deposition and etch technology, you can reduce the pitch down to 40 nanometers. If you decide to go even smaller, you can go one more round and ended up having 20 nanometer pitch. Notice that, except in the beginning when lithography is used, everything else would not require optical lithography at all. And only this one is perhaps the largest in pitch. Now that you have all these fine lines, what are you going to do to create the line segments in making the integrated circuits? Enter Siebel, which is being developed by Multibeam. This is how Siebel works. You start with the design layout file, which can easily split into line patterns and cut patterns. The line patterns, of course, is being used by optical lithography to do the printing, and followed by pitch division if needed. Siebel will simply use the cut pattern database to decide where there is a cut and do the job, and this is what happened on the wafer. At this point, I would like to highlight three important points. First, the cut pattern has very low pattern density, typically about 5% or less. This is the case for cutting poly lines in gate layers, metal lines in interconnect structure, or the fins in the FinFET devices. This low pattern density is also true for cutting contact holes and via holes, which eBeam is equally capable of doing. Second, Multibeam's vector scanning can deflect a shape beam to where there is a cut. Because cut densities only cover 5% of the wafer, we will be able to skip 95% of the wafer that we don't have to visit. And the third part is also important. Multibeam's column design enables high current density, about 10 times higher than the state-of-the-art eBeam mask writers. Now, when you put all three together, low pattern density, vector scanning, and high current density, you'll have a fast writing system to cut holes and as well as cut lines. Let me also say something about Siebel. Siebel is not a brand name. It's not a trademark. It is used just like CMOS, complementary metal oxide semiconductor. We all love that. Anybody can make CMOS devices, and anybody can build Siebel writers. Only that we believe that Multibeam's approach to Siebel would offer the most cost-effective solution to complement optical lithography in doing the cutting. Let us now examine the Multibeam approach to Siebel. This graphic represents Multibeam's path to high throughput, and I'll start on the left. The miniature column measures about 120 millimeters in height and 20 millimeters in diameter, about the size of a highlighter pen on your desk. 100 of these columns would cover the entire surface of a 300 millimeter wafer. All the columns in an array write independently and in parallel. Now, when you have a multiple column array combined with the fast writing speed that I explained earlier, you can finish one wafer in about 10 minutes, which is good for low volume production and prototyping applications. For high volume manufacturing, we would expect to integrate multiple modules in a cluster tool. Cluster tools are very common in mainstream fabs, but it works the best when each module is physically small in footprint. Our module is about the size of a regular desk, which when integrated in a cluster tool will save both cost and cleanroom floor space. In conclusion, Siebel is not next generation lithography, or NGL, and Siebel does not replace optical lithography, which we believe will continue to be the bedrock of semiconductor lithography. But Siebel is a crucial part of the litho solution going forward. Siebel enables our customers to preserve investments in optical infrastructure and reduce cost of lithography at the same time. And Siebel, we believe, is the only path for eBeam lithography to get into high-volume manufacturing. As a footnote, I call your attention to a talk by Michael Smaling of Tele-Innovations, published by eBeam Initiative in the Fine Line Video Journal a year ago in May. Mike addresses on the design part of the solution. Finally, I invite you to visit our website, multibeamcorp.com. Thank you.